So good day, everybody. Welcome to today's STMS seminar. We are very delighted to have you here, and we really appreciate all the interest and support that we have gotten from the community. This has been going for now almost 3 years, and we plan to continue it as long as there is interest, but we are very fortunate to have such a supportive and engaged community, which I think is benefits everybody in the community, particularly our students and postdocs. So I see a lot of familiar faces today, but for those of you who are new, we have 2 seminars per month. Typically, they take place the last 2 Fridays of each calendar month. In each seminar, we have 2 talks, a long-form talk by a PI or senior researcher for 30 minutes with 10 minutes of discussions, and then a short-form talk by a graduate student or postdoc. And we really appreciate if you have any suggestions for our PI speakers. Also, we appreciate if you could nominate your wonderful graduate students or postdocs to give one of our short form talks. We also accept self-nomination. So unlike what you see on the slide, if you are a graduate student or postdoc in the audience and you think you have a good story to tell, please shoot myself and Sapna an email with your CV, and we will figure out a good time for you to talk as part of this series. And some of our previous speakers actually have self-nominated themselves. And I think this is a good trait and basically skill for younger people in the audience to learn. This is something that you will have to do over and over later in your career. And we want you to do it right now if you are interested in giving a talk. So today we have the pleasure of having 2 very wonderful speakers. Our main speaker is Professor Rick Remsing, who is an assistant professor in chemistry and chemical biology at Rutgers. And Rick is originally from New Jersey. He obtained his bachelor's degree at University of Sciences at Philadelphia. Then he moved to University of Maryland to do a PhD with the legendary John Weeks. And after that, he did 2 postdocs with 2 other legends, Amish Patel at Penn and Michael Klein at Temple, before starting his own career at Rutgers. And I have known Rick, I think the first time I met Rick was 10 years ago exactly, when he was giving a talk at in our group at Princeton right after finishing his PhD. And I mean, since then, I've always been impressed by the depth and breadth of the work that he does. And he has done beautiful work throughout his career, and you're gonna hear some of that today. Our second speaker is Mr. Kevin Adams, who is a PhD candidate at University of Illinois, Urbana-Champaign in Baron Peters Group. We are very pleased and delighted to have these 2 wonderful speakers. So without any further ado, I just leave the floor to Rick to talk to us about machine learning long-range interactions in liquids, which sounds really interesting. So Rick, the floor is yours.
Thanks, Amir, and thanks for the very kind words. I really appreciate it. And I appreciate the invitation from you and Sapna for the seminar series and for organizing it for so long. It's really been, a great thing, I think, for the community too. Yeah, so I'm going to tell you some of the work that we've been doing recently on using machine learning potentials to model liquids, particularly in a way that they can treat long-range interactions and have some transferability. Before I do that, I just want to get the acknowledgements done out front. So I want to acknowledge my great group, this is a picture of the group from last summer. The group has had some changes, some new people have came, some other people have left. But we have a talented postdoc, a render, 5 talented grad students, and this summer we have 6 undergrads in the group doing some great work. I want to acknowledge funding. And a lot of the machine learning work is done in collaboration with my friend Ang Gao from Beijing University of Posts and Telecommunications. And since I don't know many of you in the room, I want to tell you about the kind of things that we do in my group first before we move on to the machine learning stuff. The machine learning is just one thing. So we have a lot of different things going on that fall broadly under these 3 headings. So we're interested in things like materials for energy applications. So we're thinking about things like liquid and solid state electrolytes, perovskites for things like solar energy harvesting and catalysis. And we're thinking about things like the role of defects in catalysis at liquid solid interfaces and these kinds of problems in energy science. We also have a big part of the group that works on theoretical astrobiology and planetary science, where we're modeling things like non-aqueous chemistry, the role of nuclear quantum effects on chemistry on cold worlds, both in liquids and in solids. And we're also doing some work on the role of mineral surfaces in aqueous geochemistry and with applications to understanding origins of life on Earth. And what I'll tell you about today is some things that fall under our kind of method development interests, where we think about things like long-range interactions, machine learning, but then we also develop things like path integral techniques to simulate excess electrons in semiconductors, in complex systems like this movie I'm showing at the bottom. But I want to talk about the machine learning work that we're doing. And most of our work is inspired by problems in energy science. And so, one of the big problems that I think all of us are aware is that we need more energy. The population of the Earth is growing constantly, right? And so we need to essentially double the rate of our energy production in less than 30 years. This would correspond to something like 10 to the 10 tons of oil per year, and we don't want to burn that much oil. So maybe we should try to come up with some clean and renewable energy sources. So things like electrochemical hydrogen production for renewable hydrogen fuel. And of course, with a lot of these renewables, especially solar energy-based renewables, the energy is intermittent, right? That you need the sun to be out to have a solar cell harvest energy. And so you need some way to store this energy in a sustainable way too. And so we need to think about things like batteries, other ways of storing energy. And so I think a lot of these goals can be met if we can design new materials, and not sort of the trial and error type design, but maybe we need some rational design principles or knowledge-based design principles where we understand what's going on at the molecular or subatomic level and use these insights to help design materials. And so these are things, like I said, catalysts and batteries like supercapacitors, pseudocapacitors, and so on. And the hope is that once we understand things that are going on at the molecular scale, maybe we can design new things. And we're not going to get to, what I'm showing here on the right, we're not going to be able to do a band structure calculation and get a better car, but hopefully that we can, understand the fundamentals of molecular systems and energy applications, and then eventually, have some impact on the way the world works. And so for me, as a theorist and someone who does molecular simulations, and I'm sure a lot of you might have the same view of what an electrochemical system looks like. So if I'll have something like a battery cell for electrochemical storage, I might have some electrodes in the system. These are these gray boxes. I have an electrolyte confined between these electrodes. Maybe I have a potential difference between the electrodes that creates an applied field. And in some cases, you can even have things like chemical reactions happening at the interface between the electrode and the electrolyte. And so in order to describe these electrochemical systems and the types of problems that we're interested in, you can't just use sort of bulk insights, so knowledge about the bulk electrolyte, to describe everything that's going on. So the structure of the system at the interface is different than the bulk structure. Because that structure is different, things like the chemistry that's happening at the interface is different than chemistry in the bulk. And these applied fields also play an important role. And so you have to consider things like how the solvent or the solutes respond to electric fields, not just with sort of collective nuclear rearrangements that give rise to things like dielectric response, but also how does the electronic structure of the solvent and the solute respond to these applied fields? So how do the molecules polarize in response to these types of interactions? And we would like to get sort of molecular details through atomic scale modeling, but this is quite a complex system, right? There's lots of processes going on. And so we need some way to do this, right? If we want to describe things like chemical reactions, we typically need clever reactive models or quantum mechanics. The same goes for electrodes. You need something that can either have charges fluctuate, or you need a quantum mechanical description. For electrostatic response to things like field, classical mechanics works pretty well, but if you need electronic response, you need some kind of either quantum mechanics or good polarizable force fields. So this, there's a lot of different fundamental problems that show up in just this sort of simple diagram. And I think we can't do this all at once now because we don't have techniques that can reach the sizes and the timescales we need to describe these systems. And that's where sort of advances in modeling come in. Right? If we want to do things quantum mechanically with something like density functional theory, we're limited to sort of the small time scale, small length scale limits. If we were able to do everything with classical molecular dynamics, you can get to the scales and time scales, length and time scales necessary for a lot of processes. But you lose, things like polarizability and chemical reactions. And so this is where machine learning comes in. So with machine learning potentials, you try to develop models that have the accuracy and sort of the predictability is probably a better way to say it, of DFT. But you're getting closer to the efficiency of MD. These machine learning potentials are still slower than classical molecular dynamics, but they're much faster than ab initio techniques. And so you get somewhere in the middle here. So it's a nice give and take between the two. And to give you a feel for how expensive these different types of calculations are, especially for the students, if you haven't carried out both types of things before, if you were doing something like this small box of water with some typical density functional approach, you might take 3 minutes to evaluate the energy for one of these configurations, whereas if you're doing this giant box of water with classical molecular dynamics, it might take a couple milliseconds to evaluate the energy. Right? And we want to move to those kind of scales, but with the DFT predictability. And that's where something called neural network potentials come in. And the idea with these neural network potentials is that you have some training data set that consists of atomic configurations and the energies and forces predicted by density functional theory or some other type of quantum mechanical method for those configurations. Those serve as sort of an input to train your neural network, which means it's learning how to predict these energies and forces from the atomic configurations in some way. And the hope then is that your neural network can then predict the energies and forces for configurations that look similar to the ones in your training set. And they can do that at a much more efficient way than just doing the DFT calculation. And that allows you to scale your systems up to larger sizes and longer timescales. And if you haven't seen neural networks before, I know this has sort of come up a lot in this seminar series, so maybe all of you have at this point, but just in case, I want to give you an idea of what a simple, what's called a feed-forward neural network looks like. This is taken from a classic paper from Baylor and Paranello. So typically you have some inputs that go into your neural network. And so this is some input from your atomic configuration. We don't use the coordinates themselves. You have some descriptors or some functions of the coordinates that go into this network. On the other end, you have the output, right, which is maybe the potential energy of the system in that configuration. And in the middle, you have this thing that sort of defines what your neural network is. And these are the hidden layers. And the idea here is that the more layers you have, the more flexible your neural network is. And for typical systems that we're dealing with, you might have 2 to 3 layers and about 50 nodes in each layer. And these layers define sort of the functional form of your neural network. So you can write down a mathematical form for the energy in your output layer that depends on all the weights between your different layers of the system. And essentially, when you're training your neural network, it's learning all these parameters in this mathematical model. right? So it's a sort of complex nonlinear fitting, if you want to think of it that way. And so these descriptor functions, right, we're not using coordinates, we're using some measure of the structure in the system. Typically, for the things that I'm going to talk about today, we use descriptors that involve radial and angular correlations. So this would involve sort of two-body structure on the left. So we're looking at, have an atom and look at the structural radially around it. And then on the, we have three-body correlations for some angular descriptions. Just to give a little bit of history of why we don't use these coordinates and how these neural network potentials came to be. Probably the first time these neural network models were used in chemistry was in 95 by Doug Dorrance group at University of Delaware, where they looked at absorption of hydrogen onto silicon. And here what they were doing is trying to learn the entire potential energy surface for this process using the coordinates of the hydrogen. But really, people didn't start using neural networks in chemistry until about 2007 with this paper from Baylor and Parinello, where they used neural networks to model liquid silicon with the accuracy of DFT. And the reason why that approach caught on and why the Dorn approach did not catch on was because the Dorn approach is not scalable. They were learning the entire potential energy surface as a function of all the degrees of freedom. And so if you scale your system up, the number of degrees of freedom are growing. And so you don't have this efficient scalability that you would like to be able to do large systems. What Baylor and Parinello did was introduce a concept of locality into the neural network. So they say that the total energy is the sum of the individual energies of the atoms in the system. And the energy contribution from those atoms depends only on the local environment of the atom. So you define some sphere around some atom of interest, and you're saying that the energy of that atom depends only on the structure within that sphere. Everything else doesn't matter. And so because you're making this assumption of locality, these neural networks are scalable, right? You can, it costs the same to evaluate this interaction in the small system that it does in the big system. And so you can do these, exciting simulations of these very large models with DFT accuracy. You can do the long timescales you need to look at thermodynamics and kinetics. So things like phase transitions and chemical reactions and the kinetics for these things to happen, right? All at ab initio accuracy. But this sounds too good to be true, right? There's got to be a catch somewhere. And the catch here is that this scalability you get comes at the cost of using short range models. So because you're making this assumption of locality, you're neglecting any long range interactions in the system, right? And so the first thing you might ask is who cares, right? We're getting, these, for a lot of these systems, we're seeing that everything works. So are these long range interactions even important? Do we need them at all, right? And in this electrochemical system, you could think that, yeah, these long range electrostatics might be important in all of these processes. And so what we're going to do today is talk not about things like electrode-electrolyte interfaces and chemical reactions, but we're going to start with understanding the physics in the aqueous solvent itself and interfaces and electric fields acting on that solvent. And so if we think about what a long-range interactions actually do, our perspective of long-range interactions dates back to van der Waals and Ben Whittam, and later with Weeks, Chandler, Anderson theory, where if you have a uniform system and you look at any particle in that uniform liquid, and you consider the effects of the long-range interactions, right? So maybe something like long-range van der Waals attractions, and the same picture holds for long-range electrostatics. You might have this red particle, and then the other particles in the fluid are going to pull it to the right with their long-range interactions. And then the long-range interactions from the particles on this side, the left side, are going to pull the particle to the left with approximately the same force. And so you have this sort of cancellation of these forces, and think of it as like a tug of war, but the rope's never moving, right? Because you're pulling the same on both sides. And so this is a good approximation in essentially every configuration of a typical liquid. And as a result, if you were to simulate something like water in the bulk with full treatment of long-range electrostatics, or if you define an appropriate short-range version of that water model. Here, this is something we call GT, or Gaussian truncated water, where we replace the 1/r Coulomb potential by this V0, this short range potential. The structure in the full system with the long range electrostatics and this short range system is the same. Right? And this is because of this cancellation of the long range interactions in these liquids. And this is one of the reasons why machine learning models with this local assumption do very well for describing the bulk structure in uniform liquids and similar environments. They also have this force cancellation, so the long-range interactions don't matter in the bulk. It turns out that if you look close enough, you can see some problems in these models. So if you look at long-range correlations in the system, you do see some issues. And of course, this might make sense, right? You're neglecting long-range interactions, and so long-range correlations might be messed up. And so if we look at dipole-dipole correlations, and this is in K space, so think of it as sort of a structure factor, but between dipole correlations. These sort of, these Fourier transforms of these correlations satisfy particular sum rules on their behavior as K gets very small, right? So K getting very small means the distance is getting very large. And for these dipole-dipole correlations, this K goes to zero limit is related to the dielectric constant in the system. For people that are familiar with structure factors, this is kind of like the K goes to zero limit of a structure factor is related to the compressibility in the system. And so if we zoom in on this low K behavior of this correlation function, it should plateau as K gets small at this green line, but instead it shoots up as K goes to zero, indicating that these sort of short-range machine learning models fail in the bulk at describing things like the dielectric constant, at least from this correlation function perspective. Where else do they fail? Right, so they fail in, or are expected to fail in non-uniform systems. So if I look at the non-uniform system, this force cancellation picture that I told you about for uniform fluids breaks down. So if I look at a particle near an interface and I consider the long-range interactions from the other particles in the system, I might have a force pulling the particle to the right, but there's no other particles to the left to pull it and cancel those long-ranged forces, right? And so you develop these unbalanced, net unbalanced forces at interfaces. If those forces are coming from attractive van der Waals types interactions, this is responsible for things like drying in molecular interfaces. And long-range Coulomb interactions have significant impacts on the orientational structure of molecular liquids at interfaces. And so here I'm showing water confined between two smooth hydrophobic walls. These are some calculations that have been done before, but the results I'm showing are new ones from like a graduate student, Atul Thakur, who's been doing some exciting work on these kind of things that you keep an eye out for. I'm not going to talk about them today. And here he's looking at the angle that the dipole moment of water makes with the surface normal. If you have long-range interactions in the system, you get this orange curve where you have some structuring at the interface, but very quickly the structuring, the cosine of the angle goes to zero, so you have no structure and you're in the uniform bulk very quickly from the wall. If you neglect these long-range interactions, you get overstructuring at the interface because the short-range model cannot properly describe the dielectric constant. It can't properly describe screening. So the water cannot screen these overstructured dipoles at the surface, and orientational ordering persists throughout the entire system. So this purple GT curve never has a real bulk, right? And so these long-range electrostatics at interfaces generate some effective torque that reorients waters in the right way to give them the right structure and achieve proper screening. And so long-range interactions are important for interfacial structure. And if you look at things like machine learning or neural network potentials at interfaces, so you take them, you train them in the bulk and just create an interface, right? So here we're just taking neural network for water that was trained in the bulk and creating a water vapor interface. You get a stable interface, but you have this problem of over orientation and the ordering persisting throughout the entire system. So there's never a real bulk in these models. And the problems don't appear just for interfaces. You can also find problems when you look at ions and applied fields. These long-range interactions are also important. So if you look at things like correlations between divalent ions in aqueous solution, right? So the full electrostatics is the black radial distribution function. And when you truncate them, this is something we're calling SC as the truncated model, you really underestimate the peaks in the radial distribution function. So you're not even getting pair correlations right in the bulk solution when you neglect long-range interactions. And I think this is particular to higher charge, so higher valence ions. So some work on things like sodium chloride has shown that they may not be important for monovalent ions. So it's important for interfaces, electrolyte structure, and then even the response to fields. And so if you look at the response to an electric field in confinement, you can't even get the bulk density of the system right. So the full electrostatics is the black curve, and the dashed line is what happens when you use a short range model and apply an electric field, which makes sense. Water can't even screen itself without long range interactions. There's no way it's going to screen and apply an electric field. So if we want to have neural network models that can respond to long-range interactions and include them in neural network models, we need a way to do this while still having the network be scalable. So the sort of approach that we take is we take our local neural network. We use this to predict a charge density in the system that we're calling rho. Once we have that charge density, we can calculate the contribution to the effective field in the system from long-range electrostatics. And then we can use that to get this effective field that we're calling E. This goes into the neural network. And now you have a self-consistent sort of iteration where now with that new field, you predict a new density, get a new field, put the field back in, and keep going until it's self-consistent. And we find in practice this self-consistency is achieved pretty quickly, right? But we need to figure out what is this charge density and how do we compute it. So the charge density itself, we get from something called maximally localized Wannier functions. For those who aren't familiar, you just need to know they're kind of like orbitals, but for periodic systems. For the experts, this is a unitary transformation between periodic block functions that you use to describe periodic systems like solids into a local basis, and everything's conserved. So the sum of the Wannier function squared gives you the charge density and all of that good stuff. If you're interested in learning more about these, check out this great review article from all of these people here. We don't use the entire Wannier functions in our approach, though. We just use the centers of the Wannier functions. And so here I'm showing what they look like for a water dimer. So this is just a dimer of water taken out of a larger system. The Wannier function centers here are these blue things. And so these give you sort of a classical point representation of where the electrons are in your system. So for water, you can see that the two lone pair Wannier function centers, and then you see two bonding pairs, right? So these are where essentially the centers of the electrons that are located on the bonds and in the lone pairs. And so our charge density that we use to input into our neural network, it consists of a sum of this electronic charge density from the Wannier function centers. So we just use them as point charges, and the sum of the nuclear point charges. So each of these nuclei has a charge, right? And so this is what we feed into our network to calculate the field. But, right, if we want to include things like electronic polarization, these molecular charge densities have to be able to fluctuate, and they have to be able to respond themselves to the long-range electrostatics. So how can we ensure that that happens? And the way that we do this is we leverage something called Cohn's nearsightedness theorem. And so what Cohn said in this theory essentially is that if you have the electron density at some point in space, to follow his notation, we'll call it O. And so this electron density at O is determined completely by the nuclear coordinates, so these red things, and the effective field within some radius RC, some finite radius. Okay? And so we can leverage this by sort of saying that, you know, the effective field that we get that goes into this nearsightedness theory consists of the external potential in the system plus the self-consistently determined long-range electric fields. So the one that we're getting from this iteration. And I think this is the crucial thing, is that, you know, this nearsightedness theory says that the density depends on both the nuclear coordinates and the effective field. So there's been some use of the nearsightedness theory in the past to just say the electron density depends only on the nuclear coordinates, but it's both, right? It depends on both the effective potential and the nuclear coordinates. And when you do this, you can make this assumption of locality in the correct effective field, and then you can include all these effects that we want to include with scalability. And so to show you what the resulting neural network actually looks like, we call it the self-consistent field neural network. It looks like this. It has two modules that we call them. So module 1 on the left here learns the positions of the 1A function centers. And we do this in 2 parts. And then module 2 learns the forces on the atoms. And we also do this in 2 parts. The 2 parts are a short range part and a long range part. And so the short range networks are more complicated. They have to take care of things like hydrogen bonding, which is much more difficult than things like long range interactions. And so the long range interaction networks are much shorter or simpler. And we do things like the short range network predicts things like the 1A functions, positions, dependent only on short range forces, and then the long range forces are included as a perturbation to those positions. And the same goes for the forces. You get the short range forces and then the perturbation on the forces from the long range interactions from that long range network. And so the key ingredient in our training that we need is we need to learn these perturbations in the 1A function center positions. And we do this by doing our DFT calculations on our training data with applied fields and without applied fields. So the configurations are all the same. We just have a uniform electric field applied in some of them to learn this delta. So let's see how this works with the last couple minutes here. So first, we should be getting the bulk structure right. Long range interactions don't matter, so it shouldn't matter what we're doing. We should still get the G of R correct. And we have good agreement between this short range Baylor-Parinello model and our new model. And the G of R's are basically the same. I did show you that if you looked at long range correlations, these short range models can mess up. So let's see if we fix that up with our model. So we can look at these long range dipole-dipole correlations. And if you look at the small k limit, I said we should get this plateau to the green line, and this new neural network does in fact plateau to the green line as k goes to 0. So it seems to be getting the dielectric screening right. To make sure it does, let's just apply a field. We can do this in our model. We have a representation of the charge density. Let's apply external fields. So if we apply something like a constant displacement field, we can get the polarization as a function of the field. And we can predict, not with a fit, what the dielectric constant should be, and we get the green line. And so we're getting, you know, the proper polarization and screening in this model. We can look at things like electronic response too. We have polarization, and so we can fix the nuclei, apply an electric field, and compute the electronic dielectric constant. We do this and we get something in very good agreement with what you would expect for water. And so we're really getting this long range electronic response in this model. So we've been trying to push it to the limit, and sort of we've been trying to break the model, and it's been working pretty good actually. So one thing Harinder did was said, okay, this is all low field, it's all linear response. Let's make it nonlinear and apply huge fields. And what should happen is that the ordering should saturate where you can't order water anymore in response to the field. And so this network produces this correct saturation of the polarization. We can separate things like electronic response from nuclear response and get some insights there. But we are producing proper dielectric saturation that agrees well at high fields with theories that are known to work pretty well. We can also use a model to gain some insights into what electronic polarization is doing. At high enough fields, it's kind of interesting. The electronic response starts to become nonlinear too, and we need to push things further. But to really push things to the limit, we can try taking this model, training it only in the bulk, put it at an interface, right, where we saw things go wrong before. And these are where long-range interactions don't cancel. And when we do this, this self-consistent field neural network produces the correct orientational structure in the system. So the short-range model has this over-screening and over-orientation throughout the slab, but this new neural network gets the correct ordering at the interface, and we get a bulk there. And the last thing I want to say is that, you know, I think this transferability is important because we may not need to have to retrain this long-range response when we put our neural networks in different situations. So if you want to put things like ions in solution or a more complicated surface, you can probably focus your training on short-range interactions. And then if your neural network has already learned long-range response, it's essentially just learning the physics of dielectric screening, and that should be transferable to all these different kinds of environments. And so that's something that we're testing out now on problems where long-range interactions and electronic effects are critically important. And so with that, I'll just leave up this sort of summary, and thank you all for listening, and I'll take any questions.
Thanks, Rick, for the wonderful talk. So let's give Rick a round of applause, and then we can just go through the questions that you might have. So if you have any questions, you can either, Sapna, go ahead.
Hey, Rick, really cool work. So I'm going to ask you a very naive question, I think. So I've seen a lot of ML-based water models, some with only short range, some with long range. Can you comment a little on how they're different? And then if, you know, someone is going into the field new, how do you decide which one to choose?
Yeah, so this is I don't know, kind of a loaded. It's not a naive question at all, right? I think that's a very good question. Everybody has their own neural network that's their favorite and their own thing. One of the things that we tried to do with this, with the two neural networks, the separation of the two, is that the short range piece, you can use whatever you want, right? So if you're using Baylor-Paranello, or you're using DeepMD or NetQuip, or whatever your favorite neural network is, you can plug that into the short range, and the long range is just something you add on top, basically. It's a pretty simple network, honestly. In terms of what the differences are, right? So the short range part, there's lots of differences with just the type of learning that people are doing and the form of the networks themselves. Some focus on using graph neural networks, some are these feed-forward neural networks, things like that. For the long-range interactions, there are a few approaches to doing this, and there's still a lot of development going on. I would say, from our perspective, I don't know, we think ours is unique in the sense that it can couple to all these different neural networks, and it includes both the sort of the electronic polarization to the long range as well as the computer. So I think it's hard to get the coupling between those two things, and this sort of self-consistent loop we have gets that coupling. Hopefully that answers some of your questions.
Yeah, for sure. Thank you.
Thank you.
So we have Aviel. So Aviel, go ahead.
Hey, Avi, how's it going?
Hi, Rick, how are you?
Yeah.
So I have a few questions. So first of all, about after you do your optimization via neural networks and you have your molecular simulation, your classical potential, does it have some nice function as a potential, or is it multi-body? Is it pairwise?
So what happens is at every configuration where the neural network evaluates the forces, right? So the functional form of the potential is the neural network.
Okay, so you cannot just write a simple function for it. In that
I mean, you
case.
could write a function for it. I had one, I can go back, but
okay.
Sorry for the quick jumping, right? So Yeah, so these neural networks have some mathematical function, right? This isn't the exact one we use, but our long range network, for example, is simpler than this actually. Yeah, so you can write down some functional forms, at least for these types of networks.
But each configuration does have its own value of the energy.
Yeah, so each so EI is the energy of a particular atom. Yeah.
Okay.
But you have to make sure, you know, all the symmetries in your system are satisfied, right? So all the oxygens are equivalent, all the hydrogens are equivalent to water, for example.
Okay. And then my other question, so all the training you did was in the bulk. That's what you said, correct?
Yeah, we didn't train anything at an interface.
Okay, and then you got the correct interface. That's what you showed on the last slide.
Yep. Yeah, I will maybe throw in one caveat there. So we are not learning the long range van der Waals attractions because we're not training at an interface and we're not including them in the training. So the density is a little lower, but the orientational ordering is correct.
Okay, so once you move to different aqueous solutions with different solutes, do you expect that you will need to retrain it for all different solutes at different concentrations, or what do you expect?
Yeah, different solutes for sure. You need to retrain. I'm hoping that this will make the training easier in the sense that you don't also need to retrain the long range part, and you really can focus on sort of training the interactions that are relevant within that local cutoff sphere. Right. So this would be things like learning that water points at OH towards an anion and points away from a cation.
Okay.
Right. So those kind of things it still has to learn. And it has to learn, you know, repulsive cores and all that stuff.
Okay. Thank you.
Thank you.
Okay, so we have Woody. So Woody, go ahead. I think he's.
So sorry about that. Thank you, Dr. Merritt. Hey, Dr. Remsing, thank you so much for the very interesting talk. We're starting to do machine learned potentials in some of our research too, and it's really awesome seeing how you can do things like this.
Thanks, I appreciate it.
I did have a couple questions for you. So first, with SCFNN, I think you mentioned this earlier. So is this a standalone package with its own graph neural net for the short range part and the long range part separate, or can you use any neural network potential like Anyquip or anything else along with this package?
Yeah, so we're the short range neural network we use is just this Baylor-Paranello network. So but you could put whatever neural network you want there, right? We don't have we have code available on GitHub that is basically very specific to this, and we're currently working to put things into labs to maybe make things a little easier for everybody.
Right. Yeah.
That want to use this. So when that's out, I mean, I can let you know or something. But
yes, please.
Yeah. So we're working on it. So we'll get it out. We're trying to figure out ways to make it as general as possible.
Awesome.
But yeah, the hope is just you can use it with any short range network you want.
Okay, cool. Awesome. Thank you. And so another question I have, so you mentioned that you don't have to do any additional training whenever you go from training on a bulk liquid water to then going to the interface, which is great. But but my question though is, how is your model aware of like these interactions with water and whatever interface you're wanting to simulate? How does it learn those interactions if it never saw it before?
That's a great point. So if you have, in this case, this is just the water vapor interface, right? So there's no surface there. But if you have something like a molecular surface, you'll have to do some kind of training to get those short range interactions right.
Right. Yeah.
Right. But the hope is that you don't have to train on sort of huge systems to get the long range interactions right, because it already knows how to do screening.
Gotcha. Okay. And then my last question for you. So for these different descriptors, one of the criteria is they have to be rotationally invariant. But whenever you put an electric field, now the orientation of your molecules, now it starts to matter. So do these descriptors, do they start to fail whenever you put an external potential on these? Or, I mean, you're showing that it gets it right, but I'm just curious, just from a I don't know, a fundamental question about atomic descriptors and the development of those. Whenever you put an electric field, they're not rotationally invariant anymore.
This is a good question. I think everything still works. I mean, if you think about an individual configuration of just a liquid itself, right? You have electric fields from all the other molecules in the system.
Right.
So
Yeah.
on average, everything is isotropic, but configuration by configuration, there is some instantaneous structure. So I think it should still work, but it's a good idea. I think maybe we should see, how, what's the way to put this? What kind of errors the neural network itself might have in some of these problems. I think is a good avenue to look at.
Okay, gotcha.
Suggestion.
Gotcha. But yeah, again, thank you so much. This has been an awesome presentation.
Thank you.
So I'm gonna ask one question from chat and then would go to Praneet to ask the last question before we move on to the next speaker. So the question that we have is, what would be the advantage of machine learning approach instead of using something like a classical evolved summation when you basically use the charges that are coming from the short range potentials?
So what is the advantage of using machine learning over just a classical model with Ewald?
Yes.
Yes. So there's several advantages. One, if you want to think of it as if you can have a purely predictive density functional, then you would have purely predictive results. So just from a theory point of view, maybe that's a nice thing to have. On top of that, right, from classical models, you're not going to get predictions of polarization unless you have some polarizable model, where this is included from the start, right? So we're allowing the charge density of the molecules to change in response to their environment. So whether they're at the interface or they're having an electric field applied, that's able to change. We're not there yet, but a lot of people are using machine learning potentials to model chemical reactions in large systems. And so that's something you're not going to be able to do with a classical potential, right? Unless you have some complicated reactive potential and then it's parameterized to essentially one reaction. But if you have, some training set of ab initio data with some series of chemical reactions, you can model them all in your simulation. So, people like Baylor, who's one of the leaders in this field, has done a lot of great work looking at things like chemical reactions on surfaces and things like proton transfer and so on. So all of these types of things you don't get out of these empirical classical models that you can get from machine learning.
So we would go then to Praneet, and this will be the last question before moving to the next speaker. So Praneet, go ahead.
Yep. Thank you, Dr. Akbari, for the chance to ask the question. And thank you, Dr. Remsing, for the wonderful talk, actually. So quick question, probably it's a very basic one. You mentioned that, ionic interactions can have a long range effect. And hence, using the short range data to train the machine learning model can be insufficient. But my question is, if the liquid is uniform, is it really important to train the machine learning model using long range data? Because in a uniform liquid, and if we do some ab initio calculations, there is also periodicity involved in it. So won't the long range ionic interactions be automatically taken into account in that case?
In the training data, they're there, right? So in the training data, the ab initio calculations are properly handling the long range electrostatics. But then when you're training your neural network potential, at least if you do it with this, traditional way where you make this locality assumption, because you're saying that the energies depend only on the local environment of an atom, then you're neglecting whatever is happening outside of that local sphere, right? And so you're neglecting any of these long-range interactions.
Okay, you're saying it's there in the training data, but it's not there in the neural network potential because you're only considering short-range interactions in neural network potential?
Yes.
Okay.
Yeah.
Thank you.
Yep. Yeah, I mean, in essence, right, I mean, these neural networks are trying to match something that's intrinsically long-ranged with short-range potentials, right? And so, there's some cases where it works, like in a uniform bulk, because those long-ranged contributions are very small, they essentially cancel. But then when you go to things like interfaces or these divalent ions in solution, the long-range part can be very significant. And so you can't match it with these short-range potentials, because if you have something like water near the interface, it's not going to know anything about the water that's a couple layers away from it, because it's outside that sort of local sphere.
Thank you so much.
Yeah. Thank you.
Okay, let's thank our speaker again and move on to the next talk, which is going to be by Kevin, who's going to talk about microkinetic models in catalysis, chic designs from wallpaper and tiles. So, Kevin, the floor is yours.
Thank you, Amir. All right, so today I want to talk to you all about microkinetic models in catalysis and to introduce a new novel method that is based on tilings of those lattices of surfaces. So in catalysis, if you want to model some sort of surface reaction, there are many different ways that you could approach that. The simplest method would be some sort of mean field microkinetic model. These are your Langmuir-Hinchewoods and your Ellie-Riddells, where you look at some sort of one specific site on the surface of your lattice, and you assume the probability of that site being occupied is equal to the coverage fraction of that specific adsorbate on the surface. And you could derive your set of rate equations and create a steady state for the coverage of the surface, and then you could derive your microkinetic model from those assumptions. And these sort of MFMKMs struggle in predicting interactions between adsorbates on the surface outside of reactions. And so these could potentially be some sort of energetic interaction between adjacent sites. And so to try and capture those adjacency interactions, you might want to move to a larger site basis, like for instance, your more complex mean fields, like your Bragg-Williams or your beta mean fields, where you will explicitly look at a set of central sites and couple those central sites to the mean field, to the coverage. And these models do improve upon the mean field microkinetic model in predicting coverage and other observables. But oftentimes with these sort of more complicated mean field approaches, you will end up with a self-consistency equation that's non-separable. And so you need to solve those sorts of equations using some sort of numerical approach. And additionally, in some more complex cases, specifically the beta or the Kikuchi, you have such a complicated set of equations that you need to make additional assumptions about other things in the system, like correlation functions, in order to even be able to solve the solution, to obtain a solution. And so using these more complicated mean field approaches can oftentimes be very inconvenient when you're dealing with real world data. And if you want to get even more accuracy, the general approach is to disregard any sort of analytical solution and to jump straight to a Monte Carlo approach, where you will explicitly define a large lattice and all the occupation states and reactions that occur on that lattice over time. And by taking a time average of certain observables on that lattice, you could then obtain a close approximation to the true ensemble averages of those observables. The problem with kinetic Monte Carlo in this case is that it's very annoying to deal with real world data. While accurate, each individual data point of the kinetic Monte Carlo needs to be simulated explicitly. And so if you want to derive a set of rate parameters from real world data, you need to simulate your kinetic Monte Carlo for each of your data points and see at what values your Monte Carlo will agree with your real world data. And so our goal here was to try and bridge the gap between the simple and easy to use microkinetic models and the highly accurate kinetic Monte Carlo models by using these tiling approaches, where we look at a small tile on the surface of this lattice and explicitly define all the states and configurations of that tile, solve a set of steady state equations for all those states, and hopefully, if our tile is big enough, we can obtain the same degree of accuracy of kinetic Monte Carlos while still maintaining a true analytical solution that is easy and separable to use, akin to that of the mean field microkinetic models. So first, to introduce the MFMKM that we'll be comparing against, our system is this simple single adsorbate dimerization system, where you can adsorb or desorb onto the surface, and two adjacent adsorbates can combine together and desorb at the same time. And so you could define your steady state equation for the coverage like follows, where you follow the probability of a site being occupied or unoccupied, and using each of the different adsorption, desorption, and dimerization rates, you can then derive your MFMKM model in the typical form that you might see as follows. And then you could obtain some sort of expression for the dimerization rate from the theta values that you would solve for in this equation above. But this simple MFMKM does not include any sort of explicit interaction between adjacent sites. And so if we want to include those, we could tag on this lambda parameter in red, which accounts for the interaction energy between occupied adjacent sites. And we could tack this lambda parameter onto the desorption rate and make it depend on the number of adjacently occupied sites for each individual site. And we could redefine our steady state equation and our MFMKM as follows. And so now solving this equation down here can hopefully get us a result for our coverage that is dependent on this interaction energy. The problem now, though, is that this self-consistency equation is now non-separable. And so we need to solve this equation numerically. And additionally, if you move to multiple sets of adsorbates, so 2 adsorbates, 3 adsorbates, etc., you end up with a set of equations that are all non-separable and coupled to each other. And so you need to solve them all simultaneously, which leads to poor scaling with the number of adsorbates. Now, to highlight the importance of including this lambda parameter and this interaction energy, I show here a comparison between the interaction case that we just derived and the non-interaction MFMKM, the standard model for these sorts of systems. And here we have some sort of lightly interacting system, and we are predicting the coverage of the adsorbate A on the surface as a function of the adsorption intensity. And we could see that our interacting model very closely predicts the coverage. That is the green line here on the curve. And the non-interacting model, if we do a least squares fitting of the non-interacting MFMKM to this these data points, these KMC data points that we're using as a reference, we find that you can get a close approximation here in blue, but the problem is that your fitted parameters are no longer equal to the true parameters of the system. You end up overestimating your equilibrium constant and your dimerization rate constant by some degree. And so using or including this lambda parameter, including the interaction energies, is important for systems where this might exist, which realistically would be most systems. And so to expand on this, we were hoping our tiling model would be able to have at least comparable accuracy to this interacting MFMKM while maintaining a functional form of this expression for our coverage or our rate equation. And so to introduce our goal with the tiling model, the idea, like I mentioned earlier, is to define some sort of tile on the surface of this lattice that we could then explicitly derive all the interconversion reactions between all possible states or configuration of this tile, obtain a set of steady-state equations for each of these configurations, and then solve those steady-state equations for some sort of equilibrium distribution of all the configurations of the tile. And then from there, we could then obtain our other observables or site average observables like coverage or dimerization rate. And so we define a set of rules in picking what sort of tile we might want to pick. First being that no site within a tile should touch its own periodic image. This is to avoid any sort of self-correlation effects between a site and itself. And additionally, no site should abut one of its neighbors more than once. And so this is to avoid unfair correlations between certain sites on the lattice. And the simplest sort of tile you might think of that will include this adjacency interaction would be a two-site tile. But the problem here is that it violates both rules. Not only is the site touching itself, the stars touches itself across its periodic boundary, but it's also touching the adjacent site multiple times across the boundary. And so you might want to expand the size of the tile. Go from that two-site tile to a three-site tile. This fixes the second rule, but it still violates the first rule. We have sites touching themselves, and so you would expand once again to get an even larger tile, this 3x3 site tile. And this tile does satisfy these rules. You can use this tile in the tiling model. There's nothing wrong here. The problem might be, though, that because we are defining a set of steady-state equations for each configuration of the system, the larger the tile, the more configurations that you might have, and therefore the more equations you need to solve when obtaining your result. And so our goal, at least here, was to find the smallest possible tile that can satisfy these rules. That way we could define some sort of minimal performance for our tiling model. And in the case of a square lattice, the smallest possible tile is this plus-shaped tile down here. It's called the Greek cross tile. This tile also has the added benefit where every site on the tile touches every other site within the tile, meaning we could further simplify our set of configurations down from looking at explicitly each site being occupied or not to just how many sites are occupied in the tile, because every site in the tile is equivalent to every other site. And so we could then get our set of configurations and our interconversion reactions as follows for each possible degree of coverage of this 5-site tile. And you have 6 different states corresponding to those. And from these, we can derive our set of steady-state equations. We basically set the arrows pointing in equal to the arrows pointing out of each of these states. The problem is one of those steady-state equations is going to be redundant compared to the rest. And so we need an additional equation in order to solve that sort of linear system. And so we set some sort of normalization equation where we set these theta values, the coverage fractions of each of the configurations of this tile. The sum of those coverage fractions is equal to 1. And so using the steady-state equations and this additional equation, we can then solve our linear system for the equilibrium values of each of the set of configurations of the tile. And then we could take a linear combination of those configurations to obtain our site average observables like site average coverage or dimerization rate. And to compare performance against the mean field model, we show the coverage of adsorbate. Again, this is the same graph as I showed earlier, where we were comparing the interacting mean field to the non-interacting mean field. And we have the mean field in green and the tiling model in blue. And we see that they both have comparable accuracy in predicting the Connect Monte Carlo results for both coverage and for dimerization rate. And we could also expand our tiling model to different types of lattices. And so for a hexagonal lattice, you could follow the same procedure we did earlier to figure out what's the minimal type of tile you might pick for a hexagonal lattice, and you'll end up with this 7-site tile. You could derive the steady-state equations, you have this additional equation, solve the linear system, and take a linear combination of your results. And we can see, once again, comparable accuracy between the tiling model and the mean field model at predicting both coverage and dimerization rate. So in conclusion, we found that traditional mean field microkinetic models can't capture adjacency interactions, but you can modify those models to include those adjacency interactions. But a product of that is that you end up with non-separable analytical equations, which won't handle multiple adsorbates and could potentially be inconvenient for data analysis. And our tiling model can produce analytical separable equations and has comparable accuracy to the mean field microkinetic models at minimum, and is easily scalable to multiple adsorbates and is able to obtain a separable result. So I'd like to thank the rest of my group, specifically John Kai, who I worked closely on this project with, and I'd like to open up to any questions.
Thanks a lot, Kevin, for the wonderful talk. So let's give him a round of applause, and please, either type it into the chat or raise your hand if you have any questions. Yeah, so I will, so Woody, go ahead.
Thank you, Dr. Amir. Hey, Kevin, very nice presentation. Could you go back to where you were showing the rate laws and for one of these tiling models?
This one? Or this one?
Yeah, yeah. So and this may be a bit of a naive question, so I don't do anything with microkinetic modeling, but this is really cool to me though. So with the mean field model, you have the lambda parameter that controls the adsorbate interactions on the surface.
Yes.
But so for the tiling, where does that show up in the tiling models?
So that will show up in your steady-state equations. So when you derive your set of equations, like I mentioned earlier, this lambda parameter shows up in the desorption rate. And so in our steady-state equations, we account for that interaction energy in our sets of desorption rates.
Okay, gotcha. Thank you. And one follow-up question I have to this. So in both the mean field and in these tiling models, you only include that interaction energy for the desorption step. Why not for the adsorption step as well?
That is a good question, and you totally can. The choice to include it on just the desorption or to include it in both or even just adsorption is a little arbitrary. You can maintain detailed bounds regardless of where you tack it on. If you wanted to include it in both, you would probably include like 50% of the energy on the desorption and 50% of the energy on the adsorption rate. We chose to include it on the desorption rate somewhat arbitrarily. Plus, our case, we were looking at mostly in positive or negative interaction energy. So in that case, you might imagine once an adsorbate attaches onto the surface, the adjacent adsorbates are holding it on. It's stabilizing that adsorbate, and so it's kind of resisting the pull to desorb off the surface in that case. You might think, okay, if you switch to a positive interaction energy, it might make more sense to then put the lambda parameter on the adsorption reactions, where it's like resisting the adsorbate from going onto the surface as well, but it really doesn't matter at the end of it.
Gotcha. Okay. But yeah, very nice work. Thank you.
So maybe I will ask the last question. So, so in this interacting mean field model, I mean, it wasn't clear to me whether it has an analytical solution or you just solve this algebraic equation numerically.
So this is the most simple solution you could obtain from this interacting mean field. So what we ended up doing is you need to solve this equation numerically. However, at least in this case with the single adsorbate, you could also just invert the equation and solve for switch your independent and dependent variables and solve for one of the dependent variables as a function of theta as well. If you do it that way, then you will end up with a separable equation. However, you can't do that once you move to multiple adsorbates. That's only possible with the single adsorbate case.
Yeah, thank you. Yeah. So with this, I mean, are there any other questions? So it looks like there isn't. So with this, I would like to.
I've got a question.
Go ahead.
Thank you, Mr. Adams, for the talk. And I had two quick questions. So the first one is, why do you think, what's your reasoning behind why the mean field microkinetic model, when you perform nonlinear fitting, gave parameters that were very far off to the kinetic Monte Carlo? And then the second question is, for your tile method, have you done any comparisons between the time that it takes to solve such models versus mean field models or KMC, and is there advantages between your model in that perspective? Because another feature of mean field is how easy it is to solve, whether it's despite it being numerical, and also how it can handle also transient kinetic, and is your system also, because it's you're solving steady state coverages, is it going to be limited to steady state cases?
Yeah, unfortunately, at least in this iteration of the tiling model, it is limited to just the steady state configurations of the system. To answer your first question, you might imagine you could take this lambda parameter and you could 1 over that lambda and multiply it onto each of these other terms, and so that closely approximates what your fitted parameter here would end up being. But you also see that they're not exactly the same, and so when you do your least squares fitting, you can't just count for that interaction energy directly in your equilibrium constant or your reaction rate constant. Specifically, why they have different functional forms is because of this one switching to that lambda in the numerator or the denominator of this side of the equation here. Your second question was about the timing of solving these systems, right?
Correct.
We found, at least in these cases, the mean field model and these minimal tilings have nearly identical computational time to solve. The tiling model, it only has 6 equations that you need to solve in the linear system, or 8 for the hexagonal lattice, and so it's really easy to just diagonalize that sort of matrix and solve the linear system that way, compared to the MFMKM. And obviously both are going to vastly outperform the kinetic Monte Carlo, which requires many thousands or millions of iterations in order to converge a solid result in predicting. If you expand the size of the tile, then you start to increase the number of states that you need to count for, and the size of your linear system will grow, and therefore the time required to solve that linear system will also grow. But at least to get comparable accuracy to the mean field, you can use this minimal tiling and maintain that computational speed equivalency.
Perfect. Thank you so much.
All right, so let's thank both both our speakers, and this will therefore be the end of the official part of our event today. We look forward to seeing you all back in 3 weeks.